on linear algebra part 3 and the content is echelon matrix. Now what is an echelon matrix? Let's move on to its definition. An m by n matrix A equal to Aij m by n. This m denotes the number of rows and n denotes the number of columns. So this matrix is said to be an echelon matrix if the following conditions are satisfied. What are those conditions? Number 1, the non-zero rows are at the top. For example, so this is your echelon matrix, and if you notice here, all the non-zero rows are at the top, right? What is the second condition? Any column which contains a leading entry of a row. What is the leading entry of a row? It is the first non-zero entry of a row. For example, for row 1, what is the first non-zero entry? It is 2, right? So the condition is any column which contains a leading entry of a row. The column 1 is containing the leading entry of the row 1. Has all entries 0 below the leading entry. It is having all other entries to be 0 below that leading entry, right? Okay. Similarly, for the row 2, first non-zero entry, that is this one. This is the leading entry for the row 2, right? And the column that is containing this leading entry, that is the second column, it is having all other entries to be as 0 below the leading entry, right? Similarly, for the third row, we are having 6 and all other entries are 0 below 6. For the fourth row, the leading entry is 2 and the entry below 2 is 0, right? And fifth row is having no leading entry. There is no non-zero entry present in the fifth row, right? Next point is the column indices of the leading entries are strictly increasing with the rows. Now what is the column indices? Column index for the first row, that is denoted by L. For the first row, this denotes the row number. For the first row, the leading entry is 2, right? And at which column it is present? In column 1. So L1 is 1. For the second row, what is the leading entry? It is 5. And at which column 5 is present? Column number 2. So the column index for the row 2 is 2. Similarly, column index for the row 3 is 3. And column index for the row 4 is 4. So these are increasing in order, right? Strictly increasing in order. So when all these three conditions are satisfied, the matrix is the echelon matrix, right? The another examples of the echelon matrix are these, right? Let's check the condition for the first one. So these are the non-zero rows which are at the top, right? Second condition, 0 entries below the leading entry, right? What is the leading entry for the first row? It is 2. And all other entries below 2 are 0. Leading entry for the second row is this one. And all other entries below this leading entry is 0. Leading entry for the third row is this one, the first non-zero entry, right? And below this, the entry is 0. Now about the column indices. Column index for the first row is, the leading entry is 2. At what column it is present? Column 1. So it is 1. Column index for the second row is, and at which column it is present? It is present at column number 3. So L2 is 3. Similarly, the leading entry for the third row is this one, right? And it is present at the fourth column. So it is 4. So these are in increasing order, right? Similarly, you can check the conditions for this matrix also. So these are the examples for the echelon matrix. Next, there is a remark. The non-zero rows of an echelon matrix are linearly independent. Why? As none of them is a linear combination of the preceding rows. For example, let A be a matrix such that on applying the row operations on A, I am getting the matrix to be 1 A, B, C, and then 0, 1 D, E, and then 0, 0, 1 F, then 0, 0, 0, 1. Let's read the remark again. The non-zero rows of an echelon matrix are linearly independent. So all these are non-zero rows and these are linearly independent, right? Because none of them is a linear combinations of the preceding ones, right? That is, none of the vectors 0, 0, 0, 1, this one, then 0, 0, 1 F, this one, 0, 1 D, E, and 1 A, B, C. None of these vectors is a linear combinations of L dot C, that is the linear combinations of the preceding vectors, right? So therefore, all these vectors are linearly independent. And when all these vectors are linearly independent and none of them is a linear combinations of the preceding ones, then what we say about that? These forms the basis of the row space of A. So this is a basis of the row space of A. What is the row space of A? Yes, it is a vector space generated by the number of non-zero rows of A. So this is all about the introduction and definition part for the echelon matrices, right? Okay, thank you.